little bit more about image, and now this notion of inverse images of sets. Okay, so we just discussed the notion of the image of a function, but now we can also talk about the image of a set, and also the notion of the inverse image of a set. Okay, so let me define this. Okay, so definition. Let f from a to b be a function. So when I write this down, I'm already implying that there are two sets, set A, set B, and then A is a domain and B is a codomain. Just by writing this, all of this is already in place. Okay, I don't have to say let A and B be sets, blah blah blah. Okay, so we have a function from A to B. Then now let S be a subset of A. Okay, let S be a subset of A, and T be a subset of B. Okay, so I'm going to define two things. Number one, for elements, for subsets of A, we can talk about the image of those of that set, and it will be hopefully what you think about. So the image of a function is just all possible outputs. The image of a set is all possible outputs when you take elements from within that set. Okay, so then the image of S. Sometimes we just write this. Okay, this is the collection of elements of the form f of A, such that A is coming from S. Okay, so these are outputs of the function. Just collect the outputs of the function, but in such a way that the inputs are coming from the set S, not outside of S. Remember, S is a subset of A, so that's okay. So that's the image of S. This is a subset of what? Who can tell me? This is a subset of what? Of B, right? This is a subset of B. The elements here are these guys. What are these guys? These are outputs. And the outputs live where? B. Yes? So the image of a set is this. Now, also you can play the game backwards. Sometimes you have elements in B, and you want to ask, are these guys coming from somebody in A? Are these the image or the output of some input? Okay? So sometimes you want to ask that question. That's what we call the inverse image of a set. So number two, the inverse image of S, of T, is going to be, okay, so we do have a notation for that. So the image of S actually, sorry, I mean, you can use that notation, but this is the one that we use typically. This is more suggested. So let me stick to that. But now this is a set, so you need to understand that this is a set, and what I mean by this is doing f of every little element in S, and then you collect that. That's a set. Okay? This is more understandable. Now the inverse image of a set, the notation is, as you probably expect, we use the inverse function notation, but it's not a function. Okay? So the inverse image of T, this is how we write it. So what is this? These are elements in A, so that when you apply the function, they go to T. Okay? So these are the elements in A, such that when you do f of A, that belongs to T. This is a subset of what? This is a subset of A. Okay? So you can use this image operation, if you will, to push subsets of A to obtain a subset of B, and then you can use this inverse image operation to take a subset of B and bring it back to A. Okay? So then another question is, if you push a set and then you bring it back, does that mean that you're gonna recover the entire set? That's one question. Okay? So if I do the image of S and then I do the inverse image of that, so do they cancel each other? Okay, there are many questions now that you can ask. So I guess before I ask those questions, let's do a concrete example. Okay. So let's see. Let's say that we have the set A, which is 1, 2, 3, 4, just to hopefully have this concept more clear. And let's say the set B is 20, 30, 40, and 2022. Okay, so I'm gonna define the function via a little picture. And then there's 20, 30, 40, 20, 22, and then we have our function f, and this is what it does. So it sends 1 to 20, it sends 2 to 30, it sends 3 to 20, and it sends 4 to 20, 22. This is a function f, okay? Now I'm gonna ask you some questions. So first find f of a, then find f of 1, 3. So by this I mean this is the image notation, okay? The image of this set, okay? Find the image of those set. Then let's do the inverse image of B. Then let's do the inverse image of the singleton 20. Which, when we write it like this, sometimes you will see people writing this, okay? But technically, it's really the set containing 20, okay? Then E, so let's do the inverse image of 20, 22, and 40. And F, let's do the inverse image of 40. And of course, this question cannot be missed. It has to be here. What is the image of the empty set? And what's the inverse image of the empty set? Right? So, empty set is a subset of every set. So, I can ask you, what's the image of the empty set and what's the inverse image of the empty set? All right, so let's see. Let's answer these things. And hopefully then these ideas of image, inverse image, they stick, okay? So again, we kind of use the same function, similar to the function notation for the image. And the reason is because this suggests the definition. If you see this and this is a set, all I'm telling you is, okay, this is a subset of B because we're going to B. And what is it? Or elements of this form. Just do f of whatever is in here and you collect those in a set, okay? That's basically what we're doing. Or possible outputs of the elements of S, that's what it is. Now for the inverse image, it's different. This is back, you have a subset of B, and then you're looking back in A, and you're seeing everybody in A, that when you apply the function goes into T. And you take those elements, and that's what we call the inverse image, okay? So all the pre-images of the elements in T. That's called the elements back in A, called a pre-image. For example, 1 is a pre-image of 20. 3 is a pre-image of 20. Okay? 20 is the image of 1 and 3, and now 1 is a pre-image of 20. Okay? All right, let's see. Image of A. What is this?
20, 30, 20, 22.
So that would be 20, 30, 20, 22. Does everyone understand this? Remember, it's all possible outputs of elements of A. Now, in this case, A happens to be what? It's the domain of the function, right? So the image of the domain is just the image of the function or the range of the function, okay? This is just the same thing as the image of the function. Notice how we are skipping 40. Why are we skipping 40? Because nobody gives you 40, right? These are all possible outputs of elements of A. Here they are. Let's see. What's the image of 1, 3? 20. Very good. So everyone understand this? You just collect f of 1, f of 3. It happens that they both are 20, so it's 20. Okay? What's the inverse image of B? So that is, again, all elements in A, so that when you apply the function, it goes to B. So what would that be? 1, 2, 3, 4, right? It's all of A. It's right here, A. In other words, the inverse image of the codomain is always the entire domain, right? Because every element in the domain goes towards the codomain. So the inverse image of the codomain is the entire domain. Okay, now it's more interesting when you get subsets of this. All right, what's the inverse image of 20? Okay, so it's 1 and 3. Again, the elements in A, so when I apply the function, they go into that set. In this case, they give me 20, right? That's what you're recollecting. So it's 1 and 3. All right, here. 4. What is this? 4. Very good. So the image, the elements in A, so when I apply the function, give me either 2022 or 40. Okay? Okay, 4 goes to 2022. Now to 40, nobody goes. Okay, then we don't write anything. Do you understand this? Okay. So how about F?
The empty set.
It's empty. Why?
There's nothing goes to 40.
Because there is no element that goes to 40. Do you understand this? Remember, the question that you're asking here is, the elements here are elements in A, so when I do F of that element, gives me 40. Well, if there is no element with that property, then this is just the empty set. Yes? So, what's the image of the empty set? Why 40? Remember, what is this? It's supposed to be elements of the form F of something coming from here. Do we have anything here? So, can we do F of something? So what is this? The empty set. Regardless of the function that you have, the image of the empty set is just the empty set. If you tell me something else, you're telling me that that element is the result of doing F of something from here. Okay? Violating the fact that it's the empty set. And so how about this? What's the inverse image of the empty set? So this will be, remember, these are elements in A, so when I do F of that, they go to the empty set. Well, the empty set has no element, right? So the inverse image of the empty set is the empty set. Yes?
Is there anything that will give you 40?
Say that again?
Is there anything that will give you 40?
That will give you 40? Yeah. No, because 40, I mean, if you think about it, the function itself has no information on 40. Okay, 40 happens to be part of B, but F itself doesn't see 40 at all. It doesn't see 40. Remember, function is a rule. And just the elements, it tells you for every element in the domain what it gives you, okay? And then you collect that, and that if that's inside any other bigger set, that's the codomain. But really, the function, the only thing that it says is the image, the range. That's the only thing. That's the only thing that the function sees. Anything else is it misses. Okay. All right. Questions? But I can ask this type of question because here I'm in the codomain, this is a subset of the codomain, so I have the right to ask you this. Now you need to tell me, no, the function doesn't know anything about it. And you tell me that by writing the empty set. Okay? Yes?
Can you ask what the image of B?
No, because by definition, so that's a good question. By definition, when you say the image of something, this something is coming from where? It's a subset of A. So just think about it this way. A function is, you have elements in A relating with elements in B. So if you have some stuff here, and then what you can do is you can push it forward and then ask what happens to this element. That's what image does. That would be the image of, those things. Now, sometimes you have something going on over here, and then you're wondering, okay, this guy is coming from what? These elements in here, where are they coming from? In A. So if you want to return back to the domain, that's what inverse image does. So if you remember from your college algebra class, the notion of inverse, what's the notion of the inverse of a function? The function has to be special, but once it's special, it has an inverse. What's the inverse? It's the opposite, right? The job of the inverse is to undo what the function does. If the function says 1 to 3, the inverse has to take 3 and send it back to 1, right? To undo the function. So the inverse is something that you take an element from here and then you ask what's on this side. So the image takes you from A to B, like a subset of A, and gives you a subset of B. The inverse image takes a subset of B and gives you a subset of A. Okay? So asking what's the image of B, it doesn't make sense. You put that and then you're going to get a compiler error. It's not going to even compile your program because it doesn't understand. We don't understand what that is. Image, it has to come from here. Inverse image, it has to come from here. Inverse image is to go back. Image is to go forward. That's why we write the arrows and so on. So we have a clear understanding directions, how we go. Okay, good. So next time we're gonna, there are questions. Like for example, if you have two subsets of A and you look at the union, right? That's a subset of A. So you could talk about the image of the union. The question is the union, if the image of the union of the images? That's one question, okay? So some questions remains to answer. For example, let's say S and T are subsets of A. Then the question is, I can look at the image of S, I can look at the image of T, and I can look at the image of the union. Remember, the union is still a subset of A, right? Then the question is, what happens here? Are these two things equal? Or maybe your subset? Which one of the two is it? Or maybe the two, okay? And of course, similarly with intersection, the same question. And then similarly with inverse image, okay? So those are the things that we're going to explore next time as well. And you're going to see that the inverse image actually is a nicer operation. Image is not so nice. When you do image, you forget stuff, okay? Because if you think about it, if you do image, you're going to be on this side, and then you kind of, once you're on this side, you kind of forget that 40 is not coming from anything in A, because you're already here. And when you're here, you see all of these guys, you say, oh, 40, you're my friend. But that 40 is a spy. It's not coming from anybody. Okay? So image, you sometimes lose information. Inverse image is a more friendly operation. Okay? But we're going to explore that onwards. All right. So if you didn't watch the videos, watch the videos. Okay? So that this stuff makes more sense. So next time we're going to do that, I'm going to talk about injective, which is one-to-one, and surjective functions. So we can introduce the notion of bijections, which is what we need for sets later on. Okay? To deal with infinite sets. All right. See you Wednesday. So, all right. So, do you have any questions before we begin? No? Okay, so last time we started talking about functions, okay? And then we talked about the definition of a function, and then we were discussing the notion of image and inverse image, okay? So let me remind you of this. So recall, remember here you have a function from A to B, so a function, okay? Then there are two notions attached to this. There is a notion of image and inverse image, and this has to do with sets, okay? So if S is a subset of A, okay, then its image under F is the following. So this is the notation, and what is this? These are all the outputs of the elements in S. Okay, so these are all elements of the form F of A, such that A is in S. Now I'm gonna do a little picture to hopefully convey this idea a little bit more. So for example, let's say that we have this scenario. This is the set A. Over here we have the set B, and then we have our function. Okay, here we have our function going from A to B. So what's the question that we're trying to do? So remember, a function is a relation. So it's a way of taking, you can think of it as a way of taking elements in A and producing elements in B. Okay? That's what a function does for you. It takes an element in A and it produces an element in B. So what we are asking is, well, okay, inside A, it could be a set. Let's call it S. Okay? And then the question that we're trying to figure out is what happens to the element in S when I apply the function? Well, to each element in S, of course, if I apply the function to each element in S, this is going to produce something in B. This is what we call, this is what we call the image of S, okay? Go this way, we will go in this direction using F. So you have a subset of A, and then you're just looking at all the outputs of the elements in S, or they of course are inside B. So you send everybody to B, you collect them, you make a set, that's a subset of B, naturally, right? That's a subset of B, and then that's what we call the image of S. Do you understand this? That's the image. Now, we can play the same game, we can play a similar game backwards. So you can start with a subset of B, and then ask, do these elements come from anybody in A? Okay, that's basically the notion of the inverse image. In other words, if T is a subset of B, then its inverse image under F is, so the notation is, we use this, like inverse, kind of inverse function notation, but this is not a function, okay? This is just a set. So the inverse image of T, what is this? These are the elements in A such that when I apply the function, they go into T, okay? They are an element of T. So these are the elements in A that go into T when you apply the function. Yes, they go to B, but what part of B? In T. Remember, T is inside of B. So again, let's do a little picture for that. So here is our A, here is our B, and we have our function going this way. Now this time, we are starting with a subset of B, over here, T, and then we're wondering, okay, are there any elements? What are the elements in A that go into T? If any, there could be none, and this could be empty, okay? But basically, this is what we are wondering. Are there anybody here? We're going backwards now. Are there any elements in here? So when you apply the function f, they go into T. Do you understand this? That's what the inverse image does. So the inverse image is naturally a subset of A. Okay? So the image of a set produces a subset of B, the codomain. The inverse image of a set produces a subset of the domain. Subset of A. You're going backwards. You okay with this? So again, think of a function as, it's just a way of taking, like a car. You go from point A to B. So take an element in A, take a passenger in A, and drop it at station B. Okay? That's what the function does. All right. So now that we have this operation, natural things, there are natural questions that we can answer. For example, what if I start with an element in A, with a subset of A, let's say S. I send it to B via the function, and then I pull it back. Do you get back what you started with? Or do you come back smaller? Or do you come back bigger? So that's the next question. So some questions now arise. Number one, so suppose, again, S is a subset of A, T is a subset of B. First, I want to know if I do this, and then this, what do I get? Okay, so let me put a box here. How does this compare with S itself? So I'm essentially, pushing S, but then going back, okay? I'm basically doing that, going back. So my question is, what should go in this box? An equal sign, a subset sign, an inclusion. Does it come back smaller or does it come back bigger? Okay, so there are three possibilities here: an equal sign, a subset sign, or four. Well, I guess, if it's any of these two, then this one will imply, but I'm saying that this is saying something else, also saying that it contains everything or is inside that. So it's a little bit stronger than just saying it's different. So, or maybe it's just that they are different, okay? So I would like to fill in that box. And then similarly, of course, the other way around. So if I have T, so question, does it make sense to do this? Remember, we're dealing here with a function that goes from A to B. T is living here, okay? Does it make sense to do f of t? No, you can only do f of stuff that's in A. You understand this? The only thing that you can do with f is pull t back. So you have to do inverse. Do you understand this? This doesn't make sense. You have to do inverse image because t is a subset of B. So I start with t, I pull it back, but then I push it forward. Again, I want to know, how do these two guys compare? Are they equal, or do we come back bigger, or do we come back smaller? Or maybe we get something totally different. Okay? So I'd like to be able to answer this question. So that's the first natural question that arises. So how do these two operations behave with each other? Okay? All right. So what do you think? The first one. So first of all, where is this? Is this a subset of A or is this a subset of B, the whole thing?
It's a subset of A.
Why?
Because it's pulling back.
Exactly. You start in A with S, right? You send it to B, that's this part right here, f of S, the image of S, but then you're taking that and putting it back to A. That's what this is doing. This is composition. Do you understand this? So you're going forward and then coming back. Good. And how about this one down here?
Subset of B.
Why?
Because you're pushing it forward now.
Exactly. You started at B, you put it back to A, and then you push it forward to B again. You understand this? So now the question is, in the first one, with this pushing and pulling, do we lose something? Or do we gain information? Or do we just have the same thing? Do we come back exactly how we started? Okay? That's the kind of thing that we want to answer. And we don't know anything about F. Of course, if F is special, okay, then we're gonna see that there are some special properties like one-to-one, on-to, and so on that guarantee certain things. Here you would like to do what you used to do in college algebra. Oh, these are the inverse functions, so they cancel and you get whatever is inside. Well, but for a function to have an inverse, it has to be a bijection. So it has to be both one-to-one and on-to. So it has to be a very special function, okay? Not every function has an inverse. So here we're talking at the set level only. So we want to do this in the most general case. Don't assume anything about the function, just that it's a function, okay? All right, so what do you think? What should be in the box? I think the easiest thing is just to think about an example, okay? So first of all, what is this? These are the elements, the images of elements of S, okay? These are elements of the form f of A where A is in S. And then when I pull them back, these are elements in A, so when I apply the function, they go into this set. But to be in this set, it means that they have the form f of A for an element in S. Yes? That's what that means. Now we're gonna write stuff down. I know it sounds a little bit confusing. So I guess another question is, if we are hoping for equality, right? Let's give it the benefit of the doubt. What's the best case scenario? That we don't lose or gain anything, so we get back exactly where we started, right? If we are hoping for equality, we should be able to argue that this guy is a subset of this, right? Or the other way around also, and the other way around also, that this guy is a subset of this. So let's see. Can we argue, for example, so for number one, again, here we are just investigating this. So, I guess claim, or let's say conjecture, because we don't know if it's true or not, okay? Maybe let's try to see, actually, let me not even call it conjecture. So is S a subset of this? Okay, so to answer this question, let's start with an element in S. Let's call it A, right? Because S is a subset of A, so let's call it little a. And let's see where we can argue that this A is also in here, okay? Now, what does it mean to be here? It means that if I do F, to be an element here means that when I do F of that element, I have to be here, okay? Well, then, if I do F of A, where is this? So I start with an element A, which is in S. Remember, S is subset of A. So if I do F of A, that goes to B, right? But in particular, this is an element in the image of S, right? Because we started with an element in S. So this is in F of S. So let me show you the picture. So here is A, here is B, here we have S, and here is the little A that I'm taking, right? Now, the image of S is here. Where does F of A goes? In here. Do you understand this? Because remember, image of S is all the images of elements in S. Do you understand this? So if A is in S, then F of A belongs to the image of S. But if F of A belongs to the image of S, then that means that A is here. Because remember, what is this? This, when you do the inverse image of something, these are the elements in A, so that when I apply the function, they go into that something. And that's exactly what's happened, right? A is in S, so A is in S, but it's also in A, right? And when I apply f of A, it goes into f of S. So A belongs to this pullback. In other words, if I send A and then I pull it back, I'm gonna come back into S. Okay? So that's basically what we're saying. So every element in S is a subset of this push it forward and then pull it back. Okay? So it follows then that S is a subset of this. So now we know that S is a subset. So in the box, so far we can say that this guy is either equal or bigger than S. Okay? So now the question is, could we come back bigger? Well, let's see. Let's try to do the other way around. So how about the other way? So how about the other way? In other words, do we then have that this, let me use capital S because we're dealing with a set, is a subset of S? Well, to prove this, I need to start with an element, a little a in here. And let's see where it leads us, okay? Maybe we get stuck, okay? So let's see. If A is an element here, what do we know? What does that mean? By definition of inverse image, it means that if I do f of A, where does it go? It goes to the image of S, right? So what this is telling me is that the image of A lands in here, okay? Now, the question is, does that mean that A is in S? Do we have enough information then to deduce that A, remember, this is what you want, to show that this left side is a subset of S? What you're trying to argue somehow is this, okay? That's what you want to deduce. So what we have here, is this enough to say that then A must be in S? Certainly, if A is in S, this is true. Yes, because by definition, if you apply f of A, it goes to the image of S. That's the definition. But is it possible for an element outside of S to land in the image of S? What do you think? Consider the following. I'm gonna pick here another one. Let's call this one X. Okay? And I just want to send it into the same output as A. Remember, two different inputs, they could go to the same output. Think about the constant function, right? Every single input gives you the same output all the time, right? So, but if this is your S, here is an element that's outside of S, but then it's going into f of S, into the same image. And here, what we're looking at is this guy. This dot is the one that we're looking at. So, this is the dot, the black dot. So let's call it B. This is the B. Okay? Because it's the result of doing f of A. Now, it turns out that because of this, it's also the result of doing f of X. Okay? But all you're seeing is B here. So by saying that B is an element of the image of S, now you cannot tell me that B is coming from this A. It could come from X. Do you understand what I'm saying? So that means that right here, we don't have the right to say A is in S. And just by thinking about it, we just constructed a counterexample. So we can see from here that this is not going to be true all the time. So not always true. So this does not imply A is in S all the time. Sometimes it does. Like for example, if we don't have this situation, if the function is 1-to-1, this cannot happen. 1-to-1 do not allow for this. Different input, they have to go to different output. That's what 1-to-1 means. If it's 1-to-1, this cannot happen, and then yes, okay. You can say then A is in S. Okay? But because we don't know it's any function, then we cannot. Now, we're saying that this is not true all the time. We need to provide a concrete counterexample. Remember, when you say something's false, give me a counterexample. Okay, here we have the idea. Now, let's make a counterexample. So, counterexample. We need to come up with an A, a B, and a function. Okay? So, And we already know what needs to happen. We need to construct a function that is not one-to-one. Okay, we want that sort of behavior. So let's suppose that A is 1, 2, 3. Let's suppose that B is 2 and 4. And then, I'm just gonna construct my function from A to B. And if you want, we can do it picture-wise, or you can just specify the values however you want. 1, 2, 3, 2, 4. So I'm gonna do it so that A goes to 2, 1 goes to 2, 2 goes to 4, and 3 goes to 2. Okay. And then of course, what I'm gonna do is this right here is gonna be my S. So then make S the set 1, 2. Okay. So I want to show that that S is not a subset. What is it? That the inverse image of f of S is not a subset of S. So let's see. Let's compute now the inverse image. So then inverse image of f of S. Let's do it by steps. So what's f of S in this example?
2, 4.
So f of S. So this is S. Okay. So then f of S is 2 and 4. Yes? Okay, now let's pull it back. What's the inverse image of f of S? It would be the inverse image of 2, 4. What is this?
1 and 2.
What is it? Remember what it is? Now look at this. It's all the elements whose output are either 2 or 4. What are they? What are they?
1, 2, or 3.
1, 2, 3, right? Do you understand this? So, is it a subset of S?
Yes. No.
No, it's bigger.
It's bigger.
There is no 3, right? S is a subset. We proved it. It better be a subset. S has to be a subset. Good. We proved it here. Okay? We're just arguing that the other way around doesn't work. So, notice that S. So, this is not a subset of S because 3 is not in S, right? Since 3 is not in S. How do I construct this counterexample? Is this exactly mimicking what we did on top? This 3 is the X. You see? And the B that I have there is this 2. Do you see what I'm saying? So, the point is that when you play this game of pushing forward and then pulling back, what happens? It actually comes back bigger. Okay? You may gain extra information that you didn't have at the beginning when you push forward and then pull back. So we just showed that S is just a subset of this, okay? But there could be more stuff in here than in S. So it comes back bigger in general. So what goes in the mystery box? Please. Okay? You push forward, pull back. What you can say in general is that this will contain S, but not necessarily. Do you understand this? Again, these exercises, these things that I'm doing is so that you ingrain yourself what these definitions are. You have to think about this on your own later, so you can really understand what these things are. Okay? All right. Now let's do it the other way around. We start at B, pull back, and push it forward. Okay? Inverse image, then find the image. What happens? Do we come back bigger? Do we come back smaller? Or maybe the same? All right? Same question. What do you think? Yes?
It might be wrong, but I think we come back to the same.
We come back to the same.
I
Okay.
might be wrong.
All right, let's see. Okay, so let's give it the benefit of the doubt. Just would be the longer discussion, but let's give it the benefit of the doubt. Let's say that the best case scenario is okay, we come back the same, right? So we should be able to argue that each side is a subset of the other. Okay? So let's try to do the same thing. For example, let's try to argue will the left be a subset of the right? Okay? So start like that. So for B, for B, the first question that we're gonna ask ourselves is, okay, is the left a subset of the right? All right. So how do we answer this question? What do we need to do? Start with an element here and somehow argue that that element has to be in T, right? What do you think should be the appropriate letter that I need to use? Should I use little a or should I use lowercase b? You can use whatever you want, but don't confuse people. Okay? We have A and we have B, capital A, capital B for domain, codomain. So when we use elements, we need to use, the appropriate letter. So which one should I pick? Lowercase a or lowercase b? Why?
Because it's in the B column.
Because this is a subset of B, right? Remember, you started B, you went back to A, but now you come back to B. Yes? So you should use lowercase b. Don't use A. I mean, you can use whatever you want, but it will be super confusing if you use little a. Okay? So let little b be an element here. And somehow, let's say we can argue that this b is in T. That's our job. Okay? All right. So now we start asking ourselves definitions. Okay, what does this mean? Remember, think of this as just being a set. Okay? Whatever. This is a set. So b is in f of this set, in the image of this set. So what does that mean? It means that b is the result of doing f of some little a, right? So then there exists a little a inside this set. Remember, this set is a subset of A, right? Because we pull it back to A. So that means that then there exists a little a inside this set such that when I do f of A, I get B. Right? That's what it means. To tell me that B is a result of this, it means that there is somebody in the A side, which is actually is inside this set, so that when I apply the function, it gives me that. Okay? All right? So now, let's spell this out a little bit more. If A is in the inverse image of T, what does that mean? Now, since this little a is in the inverse image of T, then what does this mean? What's the definition of inverse image? Think about the picture. You have T. What's the inverse image? You have T. So try not to look at. So you have T and then you do inverse image. This is the inverse image of T. So what does it mean to be an element here? What can you say for sure? Okay, it's an element of A also. Okay. So if I pick an element here, here is the A. This is the little a that we're dealing with right now. That's the little a that we found. Okay. What can you say about that little a? Other than being an element of that and A and so on. What else can you say? If I send it to B, where does it go? Can that guy go up here? Where does it go? It goes to T. That's what it means to be in the inverse image, right? It's an element that when you apply F, it goes into whatever that set is. Do you understand this? So that means that this guy will go in here, inside T. Yes? And this is F of A. That's the definition of inverse image. Do you understand this? It's like pulling back and forth. That's all we're doing. Okay? So this little a being here means that if I do f of a, it's gonna go into T. So since a is in the inverse image of T, then if I apply f to it, which by the way, what is that? What's f of a? What is it equal to? B. I mean, that's how we found the A, right? It's a result of doing, it's a pre-image of B. So then B, which is f of A, will be an element of T. So this A is in the inverse image of T, then if I apply f to A, it goes to T, right? But f of A is just B, and that's actually one. We started with B here, and then we showed that B is in T. Okay? So, yes. If you play this game, at at least this will be a subset. So what we can say for sure is that, it will be inside of T. Okay? Now the question is, could T be larger? Or will they be equal? In other words, do you get extra information? Does T have more information that this guy doesn't? So in other words, do we lose some information? The previous case, you can think of it as gaining information because you start with S and then you come back bigger. Okay? So you went and came back, but you came back bigger in general because it contains S, doesn't have to be the whole thing. So you kind of gain more information by doing that process. Now here, what we're saying here is that when you pull back and then push forward, you either come back the same or smaller. Okay? It could be that you come back smaller so that you lose information. Okay? So, what do you think? What's happening here? We are starting with T. T is an arbitrary subset of B, right? In particular, I could include there elements that do not have pre-images. Remember, your function does not have to cover the entire B. There could be guys that do not have a pre-image, right? The moment that I pull back to A, what am I doing? I'm looking at elements in A that go into T. But I'm already losing information, those that do not have pre-images. You see, if I pull back, I will not be able to see those elements that didn't have a pre-image anymore. Okay? In other words, if a function is not onto, this is going to fail. All right? So, the other inclusion. So, the other question is T a subset of this? And I will say, not in general. Now, if I'm telling you no, what do I need to do? What do I need to do? Do you just trust me, or what do I need to do? What do I need to do to convince you? How? Here we did an argument. We did a proof because we were saying that something is yes. Now, if I say that something is no, what do I need to do? I need to give you a counterexample. I have to give you a concrete situation in which this doesn't happen, and then that's it. Okay? So once again, we need to produce a function. So I need to give you an A, I need to give you a B, I need to give you a T, and then I need to give you the function. Okay? So let's do 1, 2, 3. This time, let me make B bigger. I'm gonna do, I don't know, 4, 5, 6, 7. Okay? I will pick T soon. Let me start constructing my function. So F would be a function from A to B. And 1, 2, 3. So the picture is better because with the picture you can clearly see what's going on. Okay? So I want a situation that's not onto. You're gonna see why. So let's say 1 goes to 4, 2 goes to 5, and then we need to send everybody in A somewhere. So let's do 3 goes to 6. Let's do a very nice looking function. But then there is that 7 that doesn't have anybody. Okay, that's fine. And then I'm gonna make this my T. So let's take T to be 5, 6, and 7. In other words, I want to include in T the information that we're gonna lose, which is the 7. Okay? Now what's gonna happen? Remember, we're gonna pull back. So let's pull back T. What do we get if we pull back T?
2 and 3.
We get 2 and 3. Does everybody understand this? Yes or no? These are the elements, so when you apply the function, they go into T. Yes? All right. Now, let's push them forward. So that would be the image of 2, 3. What is this?
5 and 6.
It's 5 and 6. What just happened?
We lost 7.
We lost 7. Why? Because the moment that you go back, that's it. Because F doesn't know 7. You see, F doesn't see 7. The function doesn't see 7. So the moment that you start going back to A and then you want to come back using the function, you're gonna miss this guy. So it comes back smaller. Okay? Notice that this does not contain T. In fact, since 7 is in T, but 7 is not. in this. Okay? So what we can say for sure is that it comes back small or a subset, okay? Less than or equal to. Okay? But not always they are equal. Here is an example. Okay? So these are counterexamples. So what goes in the magic box? Does it come back bigger or smaller? So in general, what we say is it comes back smaller. So subset. Okay, so again, this is the most general situation. Now, if the function is special, that now the natural question is, when do we have equality? Well, we need a special function. For example, the top will have equality if the function is 1 to 1. The bottom will have equality if the function is onto or surjective. 1 to 1 means injective, onto means surjective. And so when a function is both 1 to 1 and onto, it has a special name, an injection, injective and surjective. How do we call those functions? Bijective. When a function is bijective, then we have equality in both cases. You can go back and forth however you want. And that's when the inverse function exists. Okay? That inverse function that you used to find in college algebra and so on and pre-calculus, that only happens, that function only exists when your function is both injective and surjective. When it's a bijection. Okay? That's the best case scenario. You can go back and forth however you want. Okay, you don't lose or gain any information by looking at images or inverse images. But when your function is general, this is the best that we can hope. Did you understand this? Again, take your time later on looking at this again. And this just requires you to understand what do we really mean by this? What do we really mean by this? That's all that's happening here. Okay, definition. That's all that's happening. All right, questions? No? Okay, so we cleared that up. Now, let's see, let's call that one number 1. Okay, that was our first question. Second question. That's just, how the two operations relate with each other. Now, another natural question to ask is, how do these operations of image and inverse image behave with respect to unions and intersection? Okay, so for example, you have your function from A to B as usual. Let's think about the image first, and then let's say you have S and T. They are both subset of A. Okay, then of course the union is still a subset of A. Yes. So a natural question is, what can we say about, you can look at the image of the union, but you can also look at the image of S and the image of T, individually, and then look at their union. What can we say about these guys? What goes in the box? Do we get equality? Is it true that the image of the union is the union of the images? Or do we gain or do we lose something? What's going on here? Okay? And then we want to say a similar thing with respect to the inverse image, and then same sort of question for intersections. Okay? All right, let's see. Let's take a look at this one. So once again, let's give it, usually if you have no idea, then let's just give it the benefit of the doubt. Let's try to prove that they are equal. So how do we do that? Let's have an element here. I'll do this on the other side, and the other way around. Okay? So let's see. So okay, what letter should I use? Where are we playing? In what set are we playing? Are we playing inside A or are we playing inside B? Look at the statement. What are we dealing with? We're dealing with images. Where do the images live? In B, right? Do you understand this? This guy is in B, it's a subset of B. Right? Yes, S and T are subset of A. Yes, but when I apply the function, when I look at their image, this already was translated into B. Okay? So again, don't use misleading letters. Little b, so that you can also track yourself where you are. So then let little b be an element in the image of S union T. Okay? Now let's activate the process. What does this mean? What does it mean to be an element in the image? It means that there is a little a back home, so that when you apply the function, it gives you this b. That's what it means to be in the image, right? There is an element in A, so that when you apply the function, it gives you B. Moreover, it's not just in A, in this set, in the union, in this special union, right? So then, and again, when I say then, it means this follows by the definition, okay? So then, there exists an A in the union, such that when I do f of A, I get B. That's what it means to be an element in the image, okay? That's the definition of the image. All right, so we have this element in the union. Now remember, this is what you want to say, right? Now, well, this is pretty straightforward, because now from here, what can we deduce? So I guess, instead of writing paragraph, I think it works better if I do things formally. So let B be an element in the image, then there exists an A in the union, such that f of A equals f of B, and then here I use definition. Because now we're gonna play with a little bit of logic. So that was definition of image. Okay? All right, now what am I gonna say? I'm gonna use the definition of union. If A is in the union, what does that mean? You don't know. So what does it mean to be in the union? What's the definition of union? So how do we say it? Very good. You need to use or, not and. If you say both, then that means and. Yes, that would be intersection. So then from here it follows that A is in S or A is in T. Okay? So now to break it up, remember, it means that A is in S or in T, but now we have this extra information about A. So now we can break this down completely into logic and say and f of A equals B. Do you understand this? Remember, these are two things that are happening simultaneously. A is in the union, and it also happens that when you apply f of A, you get B. Understand this? So then I want to get down to logic. So, all right. So what we used in this step was definition of union. This is what you understand. Now, what am I going to do? I'm going to distribute, right? I'm going to distribute and over or. So then this means A is in S and f of A equals B, or A is in T and f of A equals B. Yes? I just distributed this guy. Oh, okay. So this is, I'm just going to call it logic. But what we used was distributive property, one of the standard, the basic logical equivalences. Okay. Now let's read this parenthesis. What does this mean? A is in S and f of A equals B. What does that mean? What can we say from this parenthesis? Remember what we want. Look at, always don't lose track of what we want. Can we now argue that B belongs to the image of S? Is this enough to say that B is an element of the image of S? That's exactly what it means. Because there is an element in S, so when you apply the function, it gives you B. In other words, B belongs to the image of S. It's a result of doing f of something from S. Okay? So that first parenthesis tells me that B belongs to the image of S. Okay? Or, now similarly, what does the second parenthesis tells me? That B belongs to the image of T. Right? Because in the second parenthesis it's telling me that B is a result of doing f of something from T. So it's in the image. Okay? Here we use definition of image. But then, if B is in this set or in this set, where is it? In the union. Then B is in the union. That's definition of union. Did you understand this? So we just argue that if you start with an element in the union of the image, in the image of the union, then that element belongs to the union of the image. Okay? How about the other way around? So let's see, can we trace back our steps? Can we reverse these arguments? This cannot always be done, but in this case, can we do it? My advice to you, that's why I did it this way, so I don't have to then write the second paragraph. Look at your justifications. If your justifications are entirely, do not use any assumption, nothing. If your justifications are entirely definitions and logical equivalences from logic, then this is fully reversible because definitions, they work back and forth. Okay? In other words, let's read it and see if it makes sense. To prove the other direction would be to start with an element on the right and show that it's on the left. So, this bottom line. Suppose that we start with B in here. Does that mean then that B is in either the image of S or the image of T? Well, yes, that's the definition of union. So, this naturally can be reversed. Now, can we then deduce the next line? Okay, if B is here, that means that there's an A in S, so when I do f of A is equal to B. Yes? So certainly this parenthesis makes sense. You just need to put it that exists here. But it's there. So if we say A, it's because there exists an A. And then similarly, this one translates into this. That's the definition of being an image. Okay? This B is the result of doing f of something coming from T. Okay? So we have this line. Now here, what happens from here to here? Who can tell me what's happening from this step to this one? What is it? So you are reversing the distributive property. How is that called? How do you call that in college in algebra? How do you call that? Factoring. What we just did here is factoring. When you factor something, when you factor the GCF, the greatest common factor, what are you doing? You are reversing the distributive property, right? I mean, if you have, if you have 2x squared plus 4x, you want to factor this, what do? You take out 2x, and then what do you have? So let me do this. So then what do you have? Or actually, yeah. Then you have x here and then a 2. But basically, what did you just do? You reverse the distributive property. What is the distributive property? This is 2x times x plus 2x times 2, right? And what you did was you went back. That's what factoring is when you factor out a common factor. That's exactly what we did here. Imagine that this is your times and this is your plus. Okay? Here is your plus and here are your times. We have the same thing being multiplied in both things, then you factor it out. So that's just factoring. But it's not plus of times, it's the logical connectors. Okay. And then once you are here, then of course this parenthesis turns into this one, right? Because that means that it's in the union. And then A is in the union and f of A equals B. That certainly means that then B is in the image because it's coming from somebody in the union when you apply that. Okay? So it's fully reversible. So indeed, both sets, they have the same element. That's what we just showed. Okay? So the image of the union equals the union of the images. Nothing weird happens here. Do you understand this? Okay, so let's see. Let's do inverse image. Let's see, why don't you try it? So then let's call this one, okay, number 3 now. Again, f goes from A to B. Now this time, we want to see how inverse image behave with respect to union. So we need to take two subsets of B. So let S and T be subsets of B now. Okay. Then what can we say about? So again, you can consider the union, the union of S and T. That will be a subset of B. You can pull it back to A. So what can we say about this? Pull back S first, pull back T, and then collect them in A. Okay, so here what we're doing is we're collecting them in B, and then we're pulling the entire thing back to A. Here what we're doing is we're pulling back a piece, pull back S, pull back T, and then collect them together in A. The question is, do we get the same thing? Okay, doesn't really matter when you collect. Okay, so again, I suggest giving the benefit of the doubt, try to see if you can prove it. If you get stuck, what do I mean by getting stuck? If you get to a step in which you cannot logically continue, then maybe you start to suspect, oh, probably this is not true, and then you try to look for a counterexample. And that place that you're getting stuck, that's the one that we suggest what sort of counterexample you need. Okay? Let's see, what do you think? Does equality hold? Let's see, let's just do it. So, how do we begin? What letter should I use? A or B? Which one is it? Letter A. Does everyone understand this? We're pulling back, so we are inside A. So little a. So let little a be in the inverse image of S union T. Okay, then what does this mean? So what's the definition of inverse image? This is just definitions. That's all it is. Definitions. Think about the picture. That's why I draw the pictures for you. What does that mean? It means that if I apply F, if I apply F to A, what do I get? Where do I go? I know it goes to B always, but does it go to a special place? Well, no, that's the reason why we call it inverse image. F of A goes in here, in the union. It doesn't go anywhere else. I mean, that's what it means, right? Yes, I know it goes into B. B is the whole thing, okay? But, it means that it goes into the union. It's the definition. That means that if I do F of A, it belongs to the union. Look at the picture, guys. I don't know why this is confusing. You have a subset of B. Let's call it T. And you apply the inverse image that produces this set. What's the property of this set? Look at the picture. If I do F to any element here, where do they go? T. Right? So when you do the inverse image of something, that means that will give you something here in A. So when you apply the function, it goes into this something. All right? That's what it means. Okay. All right, so that's definition of inverse image. Okay? All right, now what can we do? Again, always remember, somehow we want to narrow it down to inverse image of S and also narrow it down to inverse image of T. So that's our goal. So what can we do from here? There's only one thing we can do. So what can we do? Say that again. Use definition of union. What can you say from here? Or. This is very important. Okay, so then this means that F of A is in S or in T. I mean, it could be one of the two. We don't know, right? So you have to consider both cases. It's either in S or in T. Here we use definition of union. Yes? All right. Now, what can we say? F of A is in S. What does that mean? What can we say about A? A is an element that when you apply the function, it goes into S. So what can you say about A? No, F of A is in S. So what can I say about A? Here is B, here is S, here is capital A. You have your function going this way. And then somehow there is an A here that goes in S. That's what's happening, right? That's what we have right now in there. What can you say about this A? Does it belong to any special subset of A? If I do the inverse image of S, will it contain A? Yes, of course. I mean, that's what it means. These are all the elements in A that goes to S. Yes? Do you understand this? So this is telling me that A when I apply the function, goes into S. Well, that's what it means for A to be in the inverse image of S. That's what it means. That when I do f of A, it's an element of S. Yes? Or, what would be the other possibility?
The inverse of t.
It's in the inverse of t. Yes? One of the two. So what do we use here? Definition of inverse image, right? But if it's here or in here, where is it? The union. That's exactly what we want, right? Here we use definition of union. Yes? So we just showed that the left is a subset of the right. That's what we just showed. Now, can we reverse the arrows? Can the arrows be reversed? Let's look at your justification. Here, everything is just definitions, right? So all of these things are equivalent statements. So you can certainly go back. So these two sets, they have the same end. So we conclude that the inverse image of the union equals the union of the inverse image. So moral of the story, union is a very nice operation with respect to these two concepts. So these two concepts of image and inverse image, they behave well under union, okay? You don't lose or gain anything. They distribute nicely. What do you think is the next question that you need to think about? How do they behave with intersection? Intersection is not that nice, okay? So, so let me give you this as a homework for you to think. So homework, how about intersection? So here is a hint. I mean, it's harder if I don't tell you what's going to happen and you have to investigate it on your own. Do you want that, or would you rather tell me what it is and then you just verify it? Let's see. So just verify. And Monday we discuss it. But take your time, because why it is important? Because this allows you to really understand the concepts. Okay. So that when these things come up, then you know exactly what needs to be done. Okay. So how about intersection? So the question is, how does the image of S intersection T behave with respect to the intersections of the images? And the other question is, same thing for, of course, in each of them, you need to understand here this is a subset of A and this one is a subset of B, okay? So make sure that you made the proper adjustments. So what's the relationship? Containment, equality, just like with the union, what happens? What goes in the mystery box, okay? All right, so we stop. We went over too much.